to ask me anything about organic chemistry. Here we go. All right, so we've looked at some properties of amino acids, like isoelectric point. We discussed a little bit about electrophoresis and how it can take advantage of an isoelectric point to separate amino acids. Then we talked about the different amino acids. We looked at the 20 naturally occurring amino acids. We said that the naturally occurring amino acids are the L-amino acids. And so that brings us to the synthesis of an amino acid. How do we make an amino acid in the lab? Well, there's a few ways that we can make amino acids. Some of them are more elegant than others, but the first one that we want to cover is a reaction that was developed by three scientists, the Hell, Volhard, and Zelinsky amino acid synthesis. It says the Hell, Volhard, Zelinsky, which I sometimes just abbreviate as the HVZ reaction to make it a little simpler, is used to functionalize the carbon, the alpha carbon. So this should say the alpha carbon of a carboxylic acid. And then once you put a bromine there, so you functionalize the alpha carbon, you can do an SN2 with ammonia to make an amino acid. This is a reaction that you might remember from earlier on. We talked about the alpha bromination of a carboxylic acid. So you take the carboxylic acid, treat it with bromine and phosphorus tribromide. That makes an alpha bromo acid bromide, and then you hydrolyze the acid bromide with water, and you end up with a racemic mixture of the bromine at the alpha carbon. So that's a secondary alkyl bromide, and so that's susceptible to nucleophilic attack by a nucleophile like ammonia. So ammonia can just come in here, do an SN2, and you end up with a racemic mixture of the amino group in the alpha position. So you end up with an alpha amino acid. So that's the first amino acid synthesis that we're going to look at. Again, it's racemic. So if you wanted one, if you wanted only the D or wanted only the L, you'd have to find a way to separate those, but that's neither here nor there at the moment. The next one is one of my favorite reactions in the entire course because it's so ingenious. If you remember the malonic ester synthesis that we looked at for adding or basically making a acetic acid derivative, this is kind of in the same vein. Instead of using diethyl malonate, what we use is diethyl acetamidomalonate. So we have an acetamide here, and we still have the acidic proton here. So we can remove that proton using sodium ethoxide. That will give us the doubly stabilized enolate, and then that can act as a nucleophile with an electrophile, and we install that electrophile between those two carbonyl groups. So now we have the electrophile, but you remember that we hydrolyze and we lose carbon dioxide from one of the carboxyl groups that's formed, and we end up with only this portion left over after you hydrolyze this ester, and this amide. So you end up losing everything that's not inside this blue box, and you end up with an alpha amino acid. And since you're hydrolyzing it in an acid, you end up with the protonated form. Now, again, you end up with a racemic mixture that you'd have to find a way to separate, but it's another way of making an amino acid. I would say this is very ingenious that somebody was able to think this through. If I put an acetylated nitrogen here, I can still deprotonate, I can still alkylate, and then I can hydrolyze all three, or sorry, the two esters and the one amide group, and I'll end up with an alpha amino acid. Very, very cool synthesis, the amidomalonate synthesis. So we've got the HVZ, we've got the amidomalonate. Let's take a look at a specific example of the amidomalonate. If we take our diethyl acetamidomalonate, our starting material, we treat that with sodium ethoxide, then we hit it with benzyl bromide. Benzyl bromide is a very powerful electrophile, so we install the benzyl group. Now when we hydrolyze everything, you end up with everything that's left over inside this blue box. So what is the amino acid that we're going to have? We end up with a CH2 group here and an aromatic ring. So you might recognize that from the list of amino acids that we looked at today. This is racemic phenylalanine. I know it says it at the top. Alanine. Phenylalanine. So that's a pretty neat synthesis, the amidomalonate. Again, very, very ingenious. Well, the next one that we want to look at is the Strecker. So we've got the HVZ, the Hell-Volhard-Zelinsky. We've got the amidomalonate. And now we've got another named reaction named after another scientist, Strecker, the Strecker synthesis. And this is a two-step synthesis of an amino acid from an aldehyde. The first thing you do is you take an aldehyde, you treat it with ammonium chloride and sodium cyanide. You mix them together and you end up with what's called an alpha amino nitrile. This is your nitrile. This carbon is alpha to the nitrile and it's got an amino on it. So alpha amino nitrile. And then you hydrolyze the nitrile to a carboxyl group using acid, which is something that we saw way back in the carboxylic acids chapter. So if you look very carefully, the part of the aldehyde that's incorporated into the amino acid, maybe I can box that in a little bit better, are these pieces right here, okay? What I have in the red box from the aldehyde and in the amino acid came from the aldehyde, obviously. The nitrogen comes from the ammonium. The carboxyl comes from the nitrile after it's hydrolyzed, which came from the cyanide. So by carefully choosing your aldehyde, you can design the amino acid of your choice. And there's lots of aldehydes that are readily available. So let's take a look at an example of the Strecker synthesis. The side chain of the aldehyde becomes the side chain of the resulting amino acid. So if we have a methyl is a side chain in acetaldehyde, that's the name of this. This is acetaldehyde. Then we're just going to have an R group that's a methyl. Well, what's that? It's alanine. One of the first amino acids that we looked at was alanine. But again, it's racemic. It's a mixture of R and S. It's a 50-50 mixture. So again, you'd have to find some kind of way to separate it. Also, I think it's wise to, even though I'm not going to ask you the mechanism, you should know that it proceeds through that alpha amino nitrile. So you've got the nitrile, and on the alpha carbon, you've got the amino group like this. So this is kind of your intermediate after the first step. And then you hydrolyze the nitrile to the carboxyl group. The mechanism is shown here. I'm just going to write on this slide, will not ask you this mechanism. It's a pretty long mechanism. It's reasonable. It's very reasonable. Since you have ammonium chloride in your reaction mixture, you've got a little bit of ammonia and HCl in your reaction flask. And so that's where the ammonia and HCl come from. Anyhow, I'm not going to go over this mechanism because we have enough work as is, but if you want to take the time to go over it, you can get more of a rationale for how the Strecker synthesis works, but I'm not going to ask you anything about it on the quiz. Now, if you're wondering, you showed me a bunch of different ways to make an amino acid, and we always ended up with a racemic mixture. Everything that we did produced a racemic mixture. Is there a way to make just one enantiomer? Because when you have a racemic mixture, you got two options. You can either find a way to resolve it. So that means you're actually separating enantiomers. That is very difficult to do. A better option is to just start from the get-go and try to just make one enantiomer. Then you don't have to worry about separating anything. And so what you want to do is what's called an asymmetric synthesis. It has an asymmetry, which means it has a preference for either making the R or the S. It is much more efficient to make the desired enantiomer as opposed to getting it out of some kind of mixture. So let me show you here. This is something that was in one of the asides in chapter 8. I don't know if you remember, that's a while ago for some of you, Organic Chemistry 1. But this is part of a synthesis of L-DOPA. So take this and then you can convert it to L-DOPA, which you can look at in your own time if you want. However, if you have this double bond here, what scientists found was they could use a chiral catalyst, so it would preferentially add the hydrogen to the back face of the molecule, and therefore you only end up with one enantiomer. Now that's a pretty good deal to just get one enantiomer, right? Much better than trying to have to separate a pair of enantiomers. So you might be wondering, well, what the heck is this chiral catalyst. I've seen poisoned catalyst. I've seen Lindlar's catalyst. What's a chiral catalyst? Well, chiral catalysts are pretty complex. And a lot of chiral catalysts involve ruthenium. And this is probably the only time, as a matter of fact, that ruthenium has ever come up in this class and probably ever will. You don't talk about ruthenium a lot in organic chemistry, but ruthenium has ligands complex to it. And you might remember hearing about ligands in general chemistry too. And you end up with something that is a chiral molecule that catalyzes the reaction, to put it in. I can't come up with a better description than that, really. So it forces the hydrogen to be added to just one face of the molecule. So here's an example. This is a synthesis of diphenylalanine, which is the unnatural form, but regardless, you only get one enantiomer, and it's almost virtually all that. It says 99% enantiomeric excess. That means that one enantiomer is 99% present over the other. So what do we do when we have this double bond here? We hydrogenate, add the hydrogen specifically to one side of the molecule, and then we just hydrolyze this amide using base, and then you add some acid, and you end up with diphenylalanine. So that is a chiral synthesis. In fact, it's the only chiral synthesis that I've ever shown you. Even in Organic Chemistry 1, we didn't really go over a lot of chiral syntheses. Now, in the last couple slides, I didn't give you a really good example, I guess. No. So when we come to a question about enantioselective synthesis, I'll show you exactly what the expectations are as a Chemistry 3111 student. But I want to take some time now and take a look at a few of these syntheses, amino acid syntheses, and practice a little bit. The first one, it says, identify the reagents that you would need to make each of the following using a Volhard-Zelinsky reaction. And so we want to start out by making, what is it, leucine. Okay, and remember, this is a racemic synthesis. So let's just draw leucine. So if we draw leucine, I'm going to draw it over here because it's our product. We'll just put the amino group down here. Sometimes we like to put a little squiggle bond here, which tells you that you get a mixture of RNS. You can put it there if you want. But a leucine has an isobutyl group on it. So if we're doing the HVZ reaction, remember that it's ammonia that it's going to attack a bromine at this position. Therefore, your starting carboxylic acid would look something like this, where you have your carboxyl group. There's your alpha carbon. That's where the bromine is going to go. And then you would have to have all the other carbons in place. So you're going to take this and you're going to treat it first with bromine and phosphorus tribromide. That makes the alpha bromo acid bromide. Then you treat it with H2O. And at that point, you have the bromine installed here. I'm going to leave it out because we're going to put all the steps together. And then in step 3, we treat it with excess ammonia. Let me start over. We're going to treat it with excess ammonia, and that's going to perform the SN2, and we're going to end up with a racemic mixture of leucine. Here, and again, you can put that squiggle bond if you want. That just means you get a mixture of an RNS, or you could just write racemic, just so everybody knows that it's racemic. Let's try alanine, same rationale. We're going to draw an alanine molecule. Stereochemistry is not important because the Volhard-Zelinsky reaction is not a chiral synthesis. So here's alanine. We're going to have the bromine here. So the starting material is going to be propionic acid. 2,3 carbons, our carboxyl group, and we're going to use the exact same reaction conditions. PBr3, phosphorus tribromide, bromine, followed by treatment with water to hydrolyze the acid bromide. And then in the last step, we use excess ammonia. And again, we end up with a racemic mixture. Next question says each of the following carboxylic acids was treated with bromine and PBr3 followed by water, and the resulting alpha haloacid was then treated with excess ammonia. Draw and name the amino acid that's produced. So remember that when you're naming, you will refer to handout, unless you memorize all the amino acids, and that's your prerogative if you want to do that, no problem. So step 1 is PBr3 and bromine, followed by water. That gives us the alpha bromo carboxylic acid. So we have the bromine here. Then we treat it with excess ammonia. We replace all these bromines with nitrogens. So we end up with this. Hey, this looks familiar. Just saw this in the last problem. We end up with this amino acid. Can anybody identify this amino acid that we've made? Not a trick question. So I'll just write here, racemic. Can anybody identify this one that's got the isobutyl on it?
Leucine?
Yeah, absolutely. It's leucine. Yep, perfect. So let's just, it says name it, right? So we'll just write here, U for leucine. There we go. All right, the next one. Did anybody figure out which amino acid you would get from this one? You have an isopropyl as your R group in this one. Could anybody identify that one? I'll write down the reagents while you're thinking about it. And you can, again, refer to the handout. Could anybody identify that one? Lindsay, you identified leucine, which is a pretty tough one, I think. Oh, I'll draw the intermediate. Bromine here. Yeah, thanks, Karen. It's valine, isn't it? Yep. So we get valine. Oh, I left my positive. I don't need a positive charge there. What am I doing? It's an ammonia, Mr. Dion. There you go. That's better. So we end up with valine. All right. So we identified the amino acids that. This is a really lot of work here on the HVZ reaction. So again, this is the Hell-Volhard-Zielinski reaction. 3 steps: PBr3 with bromine, followed by water, and then excess ammonia. So let's take a look at the next one. The next one involves the amino malonate synthesis, another kind of a long one. It says, identify the reagents that you need to make each of the following amino acids. Via the amino malonate synthesis. So isoleucine, let's just draw the structure of isoleucine. That might be more helpful than anything. So if we draw isoleucine, it looks like this. So we have our, again, we're not going to worry about chirality because it's not a big deal. So it's got a sec-butyl group on it. Well, this is the part that's going to come from the acetoaminomalonate, and this is the part that's going to come from the alkyl halide, this part that I'm putting in the blue circle here. So let's start out with our ethyl acetoaminomalonate, so our diethyl acetoaminomalonate. So let's write down the structure of that. There's a lot of drawing in this one. A lot of drawing in these biochemistry chapters, like carbohydrates. You're just drawing like crazy. So we'll start out with the reagent. Then we're going to treat it with sodium ethoxide as a base. So that gives you the doubly stabilized enolate. I'll just delete that. Just that was for demonstration purposes only. Then you're going to hit it with sec-butyl bromide, like that. So let's draw a product of that. So you get the sec-butyl group jammed in there. Let's see. So we have the N with the hydrogen. We still have the acetyl group on here. And then we have the sec-butyl group on here. Now you hydrolyze it. I'm really running out of space here. So let's just write H3O plus, and then you heat that up. And again, I'm just going to kind of guide you here. You end up with the R group, the amine, which gets protonated, of course, because you're an acid, and the carboxylic acid, and that gives you isoleucine. So you end up with your carboxyl group And here's your R group over here. And then we'll just put the protonated form of the amine down here. And this is isoleucine. And of course, it is racemic. With a racemic mixture. Maybe we'll put the other ones on ice for right now. I mean, you can probably figure them out pretty quickly because alanine, and if you follow the exact same rationale, alanine is this. It's just got a methyl group. So that means you would use iodomethane. So your electrophile would just be CH3I. And for valine, it's an isopropyl. So it would look like this. This is valine. So you would need isopropyl iodide. So you could use isopropyl bromide, doesn't matter. But that's what your electrophile would be. That's the only thing that would change. Everything else would be the exact same. Is everybody with me on this one? The amino-malonate synthesis, pretty cool chemistry. Just picking out